Welcome to this TMDL public meeting for statewide beach bacteria. We're coming to you virtually as opposed to the regularly scheduled public meetings that we had planned for the first part of this year. Unfortunately, due to the COVID-19 concerns, we are canceling those meetings and we are doing this recorded video instead. This will be posted through the public notice period, which ends on May 18th. The public notice period is meant to solicit any comments to see if anybody has spotted any errors in the document or has any larger concerns or questions about the document as we move forward. If you do have any public comments after reviewing the document and hopefully watching this video, please go ahead and send those to me, Jeff Burkus. I'm the TMDL program lead. You can find my email address there. It's jeff.burkus@dnr.iowa.gov, again, by May 18th of this year. You're going to hear a little bit from me to kind of kick off this presentation, but also you're going to hear more from Jason Palmer, who's a biologist with our team. If any time you have some technical questions specifically regarding monitoring, I'd encourage you to reach out to Jason. His email address is listed there. Finally, you're going to hear from James Hallmark. He's the TMDL project lead for the statewide beach bacteria TMDL. Any technical questions that you have for him regarding modeling or the project in general, please feel free to reach out to Jim. And again, his email address is listed there. So I just wanted to make a couple statements up at the top and say, one of the benefits of having a recorded presentation like this is that at any time you can pause and go back and listen again to what we're trying to say. And so I would encourage you to do that, particularly if we get into a slide that's maybe a little bit technical and you want to hear it described again, just back up 30 seconds and see if the second time through makes a little more sense. A lot of what we talk about is fairly highly scientific. We try to do our best to relate that information in a way that we think is understandable, but we know sometimes that we deal with this stuff every day and we may not hit the mark. And so if at any point you do have some of those technical questions, really do encourage you to reach out to one of us with regards to that. So we're going to go through, I just wanted to highlight a couple things, a couple of terms that I thought were important for all of us to kind of be on the same page about. But the first slide that I have is simply a map, and this shows all of the bacteria impairments for our beaches across the state right now. All of those red little marks with writing next to them indicate a lake that has an impairment for beach bacteria. And this is something that we're going to work towards. We're going to try to do a project for each of these that will be contained eventually inside of the statewide beach bacteria TMDL. But for right now, this public presentation focuses on the areas highlighted with green circles: Nine Eagles Lake, Hickory Grove Lake, and Clear Lake. Now, it should be noted that Clear Lake has 2 beaches associated with it, so that you will find a total of 4 beaches throughout this document. One of the things that we're going to talk about is what I have referred to as the fingerprint of the solution that we're trying to push forward, the filter that we're trying to pass all of these beaches through to see if we can handle them specifically. And one of those things is what we're considering the disconnect between the information that we have gathered down at this compliance point, which is traditionally where we see a lot of our water quality information captured. And then here at the beach, where we have a specific beach monitoring program where we capture information that describes the quality of the water right in this little area here. So this is Big Creek Lake. It's not part of the study area that we have worked into this document, but it was important throughout the life of this project because it was an early participant in some of the things that we're doing for implementation. And so Jason's almost certainly going to talk in depth about this, but I wanted to just show just how far away physically the beach can be from where we traditionally take a lot of our water quality measurements. And so this is the area that we're really focusing on, is this beach area here. The next slide that I have is just a close-up of that area. And this is more just to show you exactly what we're trying to do in some of these slides. And there's a lot of information just on a map. So this is a Google image that we were able to take from Google Earth, and we were able to overlay some information on top of it with what we did. But just there's some nice things that to just kind of stop and think about. Okay, here's your compass. This shows that north is this direction. Here's a scale so that you can get an idea of how far away some of these things are from each other. And there's a little inset map here. That red dot indicates where Big Creek Lake is relative to the state of Iowa. And so there's a lot of information contained on these maps or charts or graphs. And I think it's just important to just take a second and stop and see if you can pick up any additional information that we may be trying to show you. The first concept that I think is incredibly important for us to talk about is what is a watershed and eventually a beachshed. That'll be the next slide. So this is actually Hickory Grove Lake. So this is one of our study lakes. And this shows this blue outline and everything that looks nice and sharp inside of this. This shows what the watershed area is for Hickory Grove Lake. So the way I like to think of it is if you get a rainstorm that comes across here and dumps, an inch of rain on this area, all of the rain that falls here where my cursor is outside of the watershed. We don't really care about that with regards to Hickory Grove Lake. It's not going to ever find its way into the lake. But everything that's inside of this blue outline will. So if you get rain in this area, it eventually makes its way down into Hickory Grove Lake. And so that's why we're concerned always when we're working in these projects on what's going on with the land. What type of soils are there? Do we have some erosion spots? This is the area of concern for this particular lake. As we get into the specifics of a lot of this project, what we have found is that we're most concerned with the area that drains directly to the beach. And so we've been calling this the beach shed, but basically think of it as the watershed for the beach area. And again, we'll talk more and more about this as the presentation goes on, but it's really important to remember that we are talking about a small capture zone of any type of precipitation that's going to happen in this area that's going to run down this way. If it's over here, it's probably going to enter the lake in a different fashion. And so sometimes these beach sheds are quite small. Some of them are still fairly large, but this one happens to be a very small one. And I just wanted to show the difference between this larger watershed area and the beach shed that we're focusing in on. A couple other terms that I think are important to think about here. One is the term assimilate. You might hear that word. It's kind of a fancy word for just saying how much pollutant the water can process. It's going to be a little different for every water body depending on size and a lot of different factors. Pollutants, it'll vary. But basically what we're talking about is what level of pollution can this particular water body tolerate without violating our water quality standards or the expectations that we have for them. And it leads me to my next term. You hear the word impairment a lot. That's definitely a term of art within our working world. And basically what that means is that we have collected enough information on the water quality to tell us that that water body is not meeting our water quality expectations, or you might hear water quality standards as the more official term. And so that goes on to a very official list, the 303D impaired waters list. But basically what that means is that we just have a lot of information that says that it's not meeting our expectations. And so our group comes in to try to figure out what's going on and how do we try to fix it. Another term that you might hear is point source pollution and its partner non-point source pollution. The easy way I like to think about this is that point source pollution is permitted. Anytime that someone holds a permit to be able to discharge into waters of our state, they may contain a level of pollution that we are interested in tracking, but everything that doesn't have a permit would be non-point source pollution. Now, some people will say point source pollution means you can point at it. It's very obvious. It has like a pipe coming out of a facility. In general, that is true, but I think a more accurate way to talk about point and non-point is permitted and not permitted. And you'll see throughout this project that the vast majority of what we're ever going to talk about is non-point. This is not permitted pollution. This is more runoff in these areas that's flowing over the beach and the sand into the water that we're concerned with. So just kind of a note on that. And then TMDL, which is a little bit more of a complicated term. It's the name of our program, and it's an acronym, so that's always a little bit of a challenge, but it stands for Total Maximum Daily Load. And basically, I've always liked to picture this as this picture that I've shown here with this donkey. And the way that I like to think about this is that when that cart was empty, that donkey was able to pull that cart around without any issues. As we started to stack more and more boxes on top of that cart, it got harder and harder for him to carry that cart through the street. This is obviously kind of a ridiculous point where the cart is so heavy that it has flipped him up in the air. And he obviously can't do his job and carry that cart throughout when his hose are off the ground, right? So if you think about this as the water quality, the lake, the beach area, whatever, as the donkey, and the cart as holding pollution. So all those boxes are different boxes of pollution. There is a certain amount of boxes of pollution that the lake can tolerate. It's not going to violate our standards, and it can pull that cart and still meet the standards even with some boxes on top of it. But when we put so many boxes of pollution on top of that cart, we get to the point where the lake just can't meet those expectations. And so our goal is to find what is the tipping point? What is that point in time where we have too many boxes of pollution on that cart and we need to take some of them off? So we're trying to find a number, and that number is the total maximum daily load. So it is a very specific equation that we use, and we calculate that number, and you'll find that in the document. But we also interchangeably use that term with the document as a whole, and sometimes that can be kind of confusing. And so what we've tried to do, and we're not always perfect with it, and I do it more than anybody, but we try to use the total maximum daily load as the number. And then because we've added an implementation plan inside of this, not necessarily specifics, but ideas generated to help local planning groups decide what it is that they can implement to try to improve water quality. With that information, we call that the water quality improvement plan. So there's sort of the math that you're given with the total maximum daily load, those numbers, that tipping point, however you like to think of it. And then there's information that helps in trying to plan out implementation. Those two things together, we consider that the water quality improvement plan. So one of the things I wanted to just kind of talk about was a few of the charts that you guys are going to see Jason and Jim present. And you're going to see a lot of really good information from both of these guys. And I just want to kind of emphasize how important it is to maybe slow down, take a look at it, or take a look inside the document, because there's a lot of good information on just the setup. This is going to be something that Jason might show with showing just sampling locations and how he designed that. And, this blue line indicating the water, you've got sand samples going this way, you've got water samples going this way. It's worth kind of taking the time to visualize just exactly what it was that we did, because it's going to be the foundation of something that's a little bit more advanced like this, where you see these circles where, these tiny circles basically mean that we just didn't see any evidence of bacteria in these samples, whereas something big like this big circle here, that's indicating we saw a lot more evidence of high levels of bacteria in these samples. And a lot of times we're just kind of looking for trends. And so this is important to kind of slow down and see just how many bigger circles there are around this area here. That's a really big takeaway, but it's worth kind of slowing down and seeing, okay, what is it that this very involved and complicated chart is trying to show me before just kind of moving on, because there's a lot of good information here. And once you break it down, it is pretty intuitive and it shares a lot of information. This is one that Jim might show, and this is, again, even for someone who deals with this stuff every day, this is fairly complicated and has a lot going on, and you need to kind of slow down and take your time. So this is something that, even though I've seen this a lot, I still need to slow down and kind of look at. And there's a key down here where there's a lot of good information to try to help and share what it is that we can help us discern what's above here. A couple notes, like you always want to start and look at what's written along the side here. So for here, we're talking about E. coli concentrations. And if you always want to look at the scale, and the scale is basically showing that this is a log scale. So this is 10 times more than this is 10 times more than this is 10 times more, and so it just keeps going exponentially. And then here along this scale here, this is just the month. So this is a time scale. And so if I just pick, say this one at random here, well, it's okay, what does this green diamond show? Well, this is one individual sample that we collected and analyzed, and it was analyzed sometime in the summer, because I can tell that because it's green and it's inside of this summer here. And then go down, okay, yeah, it was sometime in August, and then go over here, okay, it was a high number, right? So that's what that means. You can see these lines here. These are going to indicate different things. So they're all important to kind of take in and try to see if you can discern what these mean. Okay, so we're going to move on, and Jason, our biologist, he's going to talk about monitoring. And then Jim, he is going to finish the presentation by talking about a lot of the modeling and some of the specifics and information that we found throughout the project. Again, thank you for watching this video, and we look forward to hearing from you in the future.
Hello, this is Jason Palmer with the Iowa Department of Natural Resources. And today I'm going to share with you some information regarding a project that we put together on bacteria contamination at 3 state recreational swimming beaches. When we first initiated this project, we had a number of questions. First, we wanted to know where these impairments, where this bacteria originated from. We also wanted to know how these impairments related to the broader lake condition or the overall environmental background conditions of the watershed. And what or where the sources of bacteria that might be driving the issue. And last but not least, we'd like to determine a little bit more information about how we best manage these issues at our recreational beaches. Looking towards our data sets that we originally had when we started the project, you can see that we had an ambient beach monitoring program that covers about 34 beaches each season. These systems are sampled weekly from roughly Memorial Day to Labor Day each year. The sampling is conducted by taking a composite of 9 different sampling points within the swimming area and determining what the E. coli concentrations are. Currently, 30 out of the 34 lakes that are impaired for bacteria in the state of Iowa are impaired due to this sampling. Another piece of information that we have at our fingertips is the ambient lake monitoring data. These data points occur either at a midpoint or a deep point of one of our open lake systems, and are oftentimes quite a long distance from our beach sampling points. In addition to being spatially disconnected from the beach, we also find over time that we get very little in the way of bacteria information from these points, as they tend not to have very many reported results over the years. So in order to fill in the gap between these two data sets, we needed to come up with a monitoring scheme and a project to be able to answer a lot of our original questions. In doing that, we created a sampling design that sought to look for gradients in bacteria concentrations, both in the terrestrial zone environment and the lake environment along our swimming beaches. We wanted to see whether or not there were gradients from near to far shore in E. coli concentrations. We also wanted to see whether or not there were associations between what was happening in the terrestrial zone environment and what was happening in our near shore swimming environment, and whether or not there were differences between what was occurring in the swimming area of the lake and what was happening further out into the open lake environment. When we started the project, we wanted to select a number of locations across the state that would give us a good spread of geography and lake type. In the northern part of the state, we selected Clear Lake so that we could get something in the north that had a natural lake background. We also selected Hickory Grove Lake, which is in central Iowa and is a man-made impoundment. And then Nine Eagles Lake, which is another man-made impoundment in far southern Iowa. These sites gave us a good spread across the state of lake types and locations. Our sampling collection consisted of taking sand cores from the terrestrial environment of the beach along transects perpendicular to the waterline. We also collected water samples along these same transects, radiating out through the swimming zone and further out into the open lake. These samples were collected at 3 transects at each beach and were compared to information that was collected from other areas around the open lake environment. These sampling points in the open lake environment were situated in locations where we might expect to see runoff coming from the watershed or potentially movement in the lake body itself, currents between areas of the lake that might move bacteria within the lake system to and from the beach environment. Additionally, we established an alternate transect along a shoreline in the lake system that did not have a recreational swimming beach. The idea here is that we would take samples using the same sampling protocols that we use along the recreational swimming beach in a location that didn't have a recreational swimming beach, so we could see whether or not conditions differed between those two zones. When we look at our bacteria sampling over the course of the 2-year sampling period at our 3 sites, we saw that there were remarkably consistent results across all 3 systems. The highest concentration of bacteria we observed always occurred at the ankle-deep sampling location immediately adjacent to the shoreline. In addition to this, we found that there were distinct differences between what was observed in the swimming zone environment and what we observed in the open lake, with the swimming zone environment consistently having higher bacteria concentrations than what were observed immediately adjacent to the swimming zone out in the open lake. When we hone in on time frames where we had elevated concentrations of bacteria at the beach, or when we might have time periods where we would post for a swimming advisory, we saw that these differences became even more significant, with much higher concentrations of bacteria observed in the swimming zone and still very low levels of bacteria observed in the open lake portion of these transects. Zooming out a scale and looking at the broader lake and comparing it to these results, we saw somewhat similar results. Here at Nine Eagles Lake, from the 2 years of sampling, you can see that the bacteria concentration in the swimming zone environment averaged around 225 mpn. In the zone immediately adjacent, out in the open lake portion of the transects, we dropped to 23. And as we travel around the lake, you can see in zones where you might expect there to be runoff coming in from the watershed, or at the ambient monitoring location, and at the alternate transect, that we had relatively low concentrations of bacteria across that 2 years of sampling. Looking at a time frame when we had very elevated concentrations of bacteria observed in the swimming zone, when we would definitely have impairment level conditions in the beach. Here we had 10,500 mpn reported at average concentration in the swimming zone. Moving from the beach transects out into the open lake, you see an immediate drop off down to only 26 mpn. This drop off was drastic also when you look at where the bacteria might be emanating from. You can see that here at a watershed inlet point and at areas where we might have currents coming in from other areas of the lake, we didn't even detect bacteria in our sample. And maybe more stark of a contrast is looking at the alternate transect on this system. Using the same gradient of collection from near to far shore, we saw that our bacteria concentrations on the alternate transect fell below 10 mpn, whereas at the swimming beach, we had over 10,000. This piece of information really highlighted to us that there was something occurring in that nearshore swimming environment that was unique to the beach zone itself and wasn't occurring in other areas of the watershed. So turning our attention to the sampling that we are collecting in the beach zone itself, you can see that there were some similarities between what was occurring in the terrestrial zone environment and what was occurring in the water portion of the beach. Just like before, in the water, in the sand, we saw our highest concentrations of bacteria in close proximity to the shoreline itself. And not only did we see the higher concentrations in that zone, we also saw some pretty significant associations between the sand concentrations and the water concentrations. As the concentrations in the sand increased, we also saw increasing bacteria concentrations in the water. These associations were very strong. However, the differences in concentrations were very, very stark. When we looked at the concentration of bacteria in the sand and compared it to what we observed in the water, we had to convert our scales. And in doing so, we could show that 1 cubic centimeter of sand was roughly equivalent to 1 milliliter of water. This might not seem like a big difference. However, when you make this conversion, what we showed is that our sand concentrations of E. coli average between 500 to 1,300 times higher in concentration than what we observed in the water, with at times individual sampling trips showing that we had up to 86,500 times higher concentrations of bacteria in the sand than what we observed in the swimming water itself. What these differences in concentration showed is that there was a large accumulation of bacteria in close proximity to the shoreline that sets up a gradient of high concentration, a reservoir of bacteria that can readily mobilize and move into a relatively lower concentration water environment. Not only is this concentration gradient different because of a high to low, but we're also set up physically in a higher elevation to a lower elevation, which makes movement of material from this zone much, much easier. When we look at some of the potential delivery mechanisms that can be at play in these systems, we can see that we have a high concentration of bacteria in very close proximity to the shoreline, readily mobilized and easily moved into the water. This, not only can the material move from precipitation-based runoff, but it can also occur during dry weather conditions when we have onshore winds entraining particles of bacteria from the sand or from fecal matter deposited by waterfowl. This material can move downslope and be entrained into the swimming zone, increasing the bacteria concentrations in these areas. Additionally, we can have direct defecation by birds that might move in and out of the swimming zone environment, or potentially by children and adults running and playing and dragging material and resuspending material in this nearshore zone into the water itself. So what we've found is that we have a management issue in this zone that we need to address, and we need to target what sorts of reductions are necessary to improve the conditions within our swimming zone environment. This leads us to the next stage of our TMDL development, where we are seeking to utilize low duration curve models to look at what the assimilation capacity is of that swimming water, how much bacteria can make its way into that swimming zone environment and still maintain safe levels for recreation. From there, we can see what sorts of reductions might be necessary from our existing loads to make it so that we can improve the condition within the swimming zones. And for this portion of the project, I'm going to turn this over to my colleague, Jim.
Thank you, Jason. As mentioned, my name is Jim Hallmark, and I also work for the Department of Natural Resources. I will discuss the methods that we use to determine the maximum allowable levels of E. coli and the estimated E. coli reduction required at each swimming area. This information will be included in a report called the Water Quality Improvement Plan. This Water Quality Improvement Plan will discuss potential, in addition to those items mentioned previously, we will discuss the potential pollutant sources and calculate the total maximum daily load, or TMDL, for E. coli for the swimming areas. And then we will list and discuss some potential solutions. As Jason mentioned, three lakes were studied: Nine Eagles, Hickory Grove, and Clear Lake. We should note here that Clear Lake had two beaches that were included in the Water Quality Improvement Plan: McIntosh Woods State Park and Clear Lake State Park. Based on the work that Jason completed, we were able to narrow down the location and sources of the E. coli impairment for each of these lakes. We concluded that this would be the beach shed areas, which is a very small and limited area. The beach shed is outlined in yellow for each of the four beaches included. The beach shed areas for the four beaches range in size from 0.7 acres to 30 acres. We also identified the swimming areas at each beach, which is outlined and highlighted in red. The volume of these swimming areas ranges in size from 0.9 acre feet to 12.3 acre feet, with an acre foot being the depth of water over 1 acre. So for 0.9 acre feet, there would be 9/10 of a foot of water over 1 acre. And an acre is about the size of a football field. The swimming area was defined from the edge of sand to the edge of sand along the shoreline and extending out to a depth of approximately 4 feet, which is about a chest depth, and then extending out again 3 feet beyond that. With this information, we can begin working on a water quality improvement plan, focusing on the beach shed area and the swimming area adjacent to the beach. Since the process used to develop a TMDL for all the beaches is the same, I'll walk you through one using Nine Eagles Lake. Water quality samples were collected in each swimming area at each beach as part of the state's Ambient beach monitoring program. These samples were collected and analyzed independent of the samples Jason collected over the 2-year study. These samples go back as far as 1999 for Nine Eagles and Clear Lake and 2004 for Hickory Grove. The samples used in the analysis will date back to the earliest samples available for each lake going through 2018. I might note here too that the swimming area might also be referred to as the near shore beach volume. Once a water body has been identified as impaired, we will need to generate a water quality improvement plan. We begin by analyzing the water quality data that has been collected. In this analysis, we will plot the concentration of E. coli along the x-axis and time across the E. coli along the y-axis and time across the x-axis. The time units will be by month. This will help us to identify the time frame when the E. coli concentrations are the most problematic and exceed the allowable limits. Also, it will allow us to break up the time frame into 3 separate and distinct seasons, with spring, summer, and fall. Spring samples are those samples collected between March 15th and May 23rd. Summer samples were collected from May 24th to September 7th, and the fall samples were collected between September 8th and November 15th. We've extended the summer samples 1 week on each end to be able to include the Memorial and Labor Day holidays in the summer samples. From here, we can plot the allowable limit, in this case, a concentration of 235, highlighted in green. From there, we plot our spring samples. Again, these are individual data points or samples collected between March 15th and May 23rd from the year 1999 through 2018. The existing loading for 9 Eagles Lake is plotted as this black dotted line. The existing load is the 90th percentile ranking for all of the spring samples. This shows that the existing loading for the spring season is below the allowable concentration of 235. Next, we can plot our summer samples. The existing loading for the summer season is also plotted, which is represented by this red dotted line. As you can see, it is above the allowable concentration of 235. The difference between the existing loading and the allowable concentration is the reduction required, is the E. coli reduction required at this beach. Then we can plot our fall samples. Again, the existing loading for our fall samples is this black dotted line, which falls below our allowable concentration of 235. As you can see here, the majority and bulk of our samples were collected during the summer season, which is most likely when people will be recreating at the beach. Presenting this information in a different form, we can put it into a table. This table here represents the loadings at 9 Eagles Lake as a concentration. As I showed before in the graph, that the existing loadings during the spring and fall fell below the allowable limit of 235. And that's reflected here in the table, with the summer loading exceeding the allowable limit of 235. The difference between observed loading or existing loading and the allowable loading is this departure. That represents the amount of E. coli concentration that we must reduce along this beach. Which is a reduction of roughly 54% of the observed loading. These other values we'll talk about a little bit later as well. This bottom graph or table is the same information, just provided in a different format. Instead of a concentration, it is the mass or total loading at 9 Eagles Lake Beach. The total loading or mass loading is the concentration multiplied by the volume of the swimming area. And we get the same results, a required reduction of roughly 54% of the total loading of E. coli at this beach. So what is a TMDL? This slide shows a definition, an EPA definition of a TMDL, or total maximum daily load. Guess in short, it is the amount of a pollutant that a water body can assimilate and still meet water quality standards. So there's some math that we have to do. But before we discuss the math, we will discuss some of the potential sources of E. coli. The potential sources of E. coli can be broken into two categories: point sources and non-point sources. Point sources are those that require a discharge permit. They have effluent limits attached to these permits with a maximum allowable limit of discharge, of what they can discharge in their effluent to any receiving stream or water body. A typical point source would be a publicly owned wastewater treatment plant. But as we mentioned, our beachhead areas are a very small and limited area, and there are no point sources located within this beachhead, with any of these beachhead areas. The other source are non-point sources. Those would be anything that would not require a permit. Could be a runoff, it could be direct deposition in the lakes from waterfowl or domestic pets or wildlife, and even retention of E. coli in the sand environment. But basically anything that would not require a permit. We can look at a TMDL and compare it to our household budget. We have our spending and an existing budget. At some point, we would like to look at our spending habits and compare it to our income. If our spending habits exceed our income, it will be necessary for us to adjust our spending habits in a way so that we don't spend more than what we're bringing in. As we look at our budgets, we can divide our spending into three different categories. First, we have our fixed costs, or fixed bills. Those would be like rent, insurance, and other expenses that stay consistent from month to month. Then there would be our variable costs or variable bills. This could include groceries, clothing, entertainment, or other bills that we pay that the amount we paid varies from month to month. And then there would be those unexpected costs, things that we put into savings to account for unexpected home repairs or car repairs. So as we look at those categories and make adjustments in our budget, we eventually achieve our goal of our spending not exceeding our income. Well, a TMDL can be compared to that. We have our pollutant and we have an existing load. At some point in time, we want to compare the pollutant levels in our water body. And if those pollutant levels exceed our water quality standards, then we'll need to make some adjustments to bring that water body into compliance with water quality standards so that the pollutant levels do not exceed those standards. Just like in our budget example, we have fixed costs, variable costs, and unexpected costs. Our fixed costs in a TMDL are those point sources. The point sources have a maximum allowable limit to what they can discharge. It stays the same from month to month. Then we have the non-point sources. They vary depending on what's going on in the watershed, what's going on with the weather, and all other different types of factors. And so that could change from week to week, even month to month. Then we have a margin of safety, a safety factor to account for things that we had not considered or that we just were not aware of. As we work together as a community, as property owners, as landowners, businesses, local agencies, we can work together to achieve our water quality standards. Putting this all into an equation form, we have our budget, which is allowable budget is equal to our fixed costs or bills plus our variable costs or bills and our unexpected costs or savings. The TMDL is similar. We have our point sources, which are constant and fixed, plus our non-point sources, which are vary from month to month. And then our margin of safety or safety factor. Note that our point sources sometimes are referred to as waste load allocations, while our non-point sources are referred to as load allocations. And again, then we have the margin of safety or our safety factor. So putting this together for 9 Eagles Lake, we have our TMDL, which is equal to the total waste load allocations, our fixed costs or fixed loads, plus a summation of all our load allocations, our non-point sources, and then a margin of safety. We know that the allowable load is 230, a concentration of 235, or in a mass, as shown here in parentheses. We know in all 4 of these beach areas that the waste load allocation, or the point sources, there are none, so they equal 0. Our margin of safety is 10% of our allowable load. And the difference between our allowable load and our margin of safety gives us our load allocation. Putting all this information together, we have 4 tables representing each of the beaches. We've already talked and shown the table for 9 Eagles Beach. Again, these are all concentrations. In McIntosh Woods, we see that that beach area does not meet water quality standards in the summer months. While at Hickory Grove, that beach area does not achieve water quality standards at any time during the recreation season. And at Clear Lake, water quality standards are not achieved during the summer and fall. And we see the reduction required at each of these beaches. This is the same information presented in a different form. Previously shown as a concentration. This is the total load, which is the concentration multiplied by the volume of the swimming area at each beach. It has the same results in reduction amounts. It's just presented in a different format, as it being a total load or a total mass as opposed to a concentration. And finally, we get to an implementation plan. Here's some ideas and suggestions on how to achieve E. coli reduction in those beach areas. One of those activities is raking activities or grooming strategies. This is a picture of a beach being groomed or raked. This is at McIntosh Woods State Park. Beach raking or grooming is the practice of removing debris and other material from the beach environment. It typically includes pulling a mechanical rake behind a tractor. The rake is on a rotating mesh belt with tines that extend into the sand, picking up debris and other material. The mesh belt allows the sand to fall through back to the beach, and the debris is deposited into a hopper where it can be disposed of. This is just one method to help clean up the beach environment and reduce E. coli in the swimming area. We'd like to thank you for listening and watching this presentation. If you have any questions regarding this or the Water Quality Improvement Plan, feel free to contact Jason, Jeff, or myself at the phone numbers and email addresses listed here on this slide. Thank you again and have a good day.